This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 147. Hope your summer's off to a good start. As we were talking about, it's a smoky day here in the Northeast. But today, our presenter is John Forsythe, Senior Research Associate at CERA. The presentation is multi-satellite water vapor and derived products for forecasters. So very relevant topic for this time of year, and really any time of year. Our facilitator, Chris Gittro, meteorologist in charge from the Weather Service Forecast Office in Albany. Glad to have both of you with us today. Just a few reminders before we get started. As you just heard, this session is being recorded, and as always, there will be an opportunity for Q&A after the presentation. If you have signed in with your office account, please note your full name when asking a question in the chat. We can follow up if necessary. And of course, we will take the questions from the chat. But if you have something that you'd like to ask aloud or contribute to the discussion, feel free to just note so in the chat, and then you can unmute as Chris calls on you. Also, if you're missing your TowerS communications, check your spam folders. Unfortunately, that's happening all too common these days. And if you're willing to be a future presenter for us, please contact our TowerS team, Rashad Bowman and Emily Maddox. We'd love to have you, even if your presentation is not directly related to satellite. Maybe in future weeks, we'll have somebody talk to us about the operations related to smoke and the use of the smoke products from satellite in the decision support services and other services that we've provided in our weather service offices here in the Northeast. The training team can help create training materials that may be unavailable. Please contact Brian Mata, the Office of the Chief Learning Officer, for information and questions regarding that. I'd like to thank our TowerS team, particularly Kashad, Emily, Lee Byerly, the Office of Chief Learning Officer, the satellite programs, and all of you for being with us today, and of course, our facilitator and presenter. So without further ado, let's jump right into it. John Forsythe received his master's in atmospheric science in 1993 from Colorado State University. He has supported and led remote sensing projects for NOAA, NASA, DoD, and the private sector, with an emphasis on infrared and microwave remote sensing of water vapor and clouds. He's currently leading the transition of the Advected Layer Precipitable Water, or ALPW, into NWS operations this year. John, we're glad to have you back at the book club.
Thanks, thanks, Jordan, and thanks to the book club for having me. So yeah, I'm going to talk about these water vapor products for forecasters. Just a little bit of background on water vapor in general and where we are with transitions to operations and some new products. So, but first, I really need to acknowledge all of our team here. Especially Sheldon Cusselson, who about a year ago we sort of did one of these together. He's at the FAIR experiment right now, the flash flood experiment at WPC. So he's really been a strong connection for us to the Weather Service with all of his experience. The many forecasters who collaborate with us, and the MERS team, the microwave sounding team at NOAA, that puts the satellite soundings together, that are really the backbone of these derived products. So just as a little bit of background, there's plenty of paper literature coming out just constantly about how the precipitation is increasing, extreme rainfall, atmospheric rivers in the Arctic, the TPW is increasing, and just as a background to that, the global mean of total precipitable water, TPW, is about 1 inch right now, 26 millimeters. And globally, we're observing about a 1.5% per decade increase over the global oceans. A little different over land, but that's a good number over the ocean. And just to kind of to give the scale, the highest I've ever observed working on this for 20 plus years is about 91 millimeters, 3.5 inches, which is from Hurricane Katrina, actually. So never seen a value higher than that. But it is increasing, at a constant rate lately. So just kind of the big picture. This was a really fascinating measurement, I thought, from a a mission called Aquarius, which was a NASA low-frequency microwave mission, which could measure ocean surface salinity, which is a very difficult measurement. And fortunately, it doesn't affect the microwave remote sensing we do for water vapor, but it is measurable at like below 10 gigahertz frequencies. And you can see these red areas are areas with much higher salinity where there's more evaporation. So basically what these water vapor products that we're developing from satellites do is, as the quote there says, the source of water vapor is evaporations over the ocean. So we really need to make these observations, especially over the oceans, and then show how that water vapor is flowing into a particular weather forecast situation that may be experiencing heavy rainfall. So we've made these observations really since the early days of satellite observations. There's microwave, at least total column measurements, even in the 1970s for some brief periods of time. The profiling really came about in the 1990s. And if you want a lot more detail, we did publish an article last year in the JPSS Science Digest. We called it Inspecting the Plumbing of the Atmosphere with these multi-water vapor sources. And those 4 panels are there are the ALPW, the Advected Layer Precipitable Water product, which I'll talk about a little bit more. Just some typical uses of these. These are both from mesoscale precipitation discussions at WPC, very common users of these products. On the left here, we have the total precipitable water for an atmospheric river coming into California, actually on March 9th. I'll talk about that case a little more later. And these blended products using microwave retrievals from many low Earth orbiting satellites really are great for sort of mapping the flow of these of this moisture coming in from offshore. And then similarly, the layer precipitable water data is also used. This is a different case on the right here, but to look at how that moisture is flowing. So as I said, I kind of think of it as the plumbing. It's how big are these pipes that are delivering moisture to a weather event, and how are they going to? Is there an end in sight? Does the pipeline just keep flowing? How is that water vapor flowing? So these are things forecasters really look at. Well, today I had to say something about smoke because that's the big weather story. But I guess the good news from my perspective is the microwave data is really totally unaffected by smoke. Can measure a lot of things, but not smoke. So this is over the Northeast U.S. this morning, the 700 to 500 millibar water vapor, and there's no missing areas at all where the retrievals didn't converge, and it does show this very sharp boundary, which also shows up in the GOES data. Precipitation is our big hindrance with microwave remote sensing. We can't do the vertical profile of water vapor in those areas, but no problem with smoke. So at least there's a little more mid-level moisture over the Northeast. Hopefully that can get translated into some precipitation. So just a bit of a status update on these 2 products, which are really independent products, even though they share some of the sensors. We process them independently, and the science is different in each one. So blended TPW is, I think everyone who works at a WFO will be familiar with this, became operational way back in 2009, but we're doing quite a few enhancements right now. It's a new version 4, and it should be available in AWIPS 2 in early 2024. So it's really the first big science upgrades in 10 years. It's going to use goes east and west in clear sky areas. It's going to use something called Mimic, which is kind of like the ALPW product. It's an advected Total Precipitable Water product developed by Tony Wimmers of SIMS, who I'm teaming up with on this transition, and also GPS data over the CONUS, which it uses now. So should see those come online in early 2024, and then on a little different schedule, which is a brand new product, the ALPW. should become operational in late 2023. There was a bit of a delay with other priorities that the NESDIS, so what's called the assist team, which is the transition team that works on all kinds of algorithms, not just these, getting them into the cloud. But in the interim, CIRA distributes ALPW to WFOs and NHC, WPC. Chris just told me this morning they were looking at it in Albany, so they have it there. So if you're at a WFO and you would like the ALPW product, you can send me a note after the meeting. We can add you to that and get it out through our LDM. So thinking about what these blended products do, we're taking a lot of satellites and putting them together, and really what we're trying to, I guess, mimic is what we would have if we had a geostationary microwave instrument. When I started in the field in the early 90s, there was a lot of talk that this might happen. Here's the first paper on that from 1985 with some well-known names on that from NASA. But so the concepts have been around, but I think I'd have to say it does not look like we're going to see one in the next decade from anywhere. But with a mixture of these larger low Earth orbiter satellites, things like JPSS, small sats, and then using advection techniques where warranted. And I say that because not everything is suitable to advection, at least on longer time frames. We can begin to approach this capability. So, there was some good technical reasons why this didn't happen. The early designs where you would need like something like a rotating 4-meter diameter antenna. So that was a big challenge. There's programmatic reasons of, well, who's going to do this experimental sensor in geostationary orbit when most of the NASA experiments are low Earth orbiters. So nevertheless, I don't think we'll see this, but we have products that are very similar to what we might have seen from a geostationary microwave sensor. And just as a bit of a list here, these are upcoming small sat missions which have a profiling capability for water vapor. NASA Tropics, just I'll mention that. There was a seminar, Satellite Book Club, a few weeks ago on that from Patrick Duran. Just launched 4 spacecraft in May, so that's off and running. Something called INCUS, which also includes another microwave radiometer as well as active sensors. That's about convection, kind of that's a very interesting experiment. EUMETSAT has something called the Arctic Weather Satellite Program and the Sterna program, which is going to support these small sat sensors. And then there's commercial companies, Tomorrow.io, which may not be real time necessarily, but could still probably help out with some of the science with these products. So as I said, there's certainly the big reliable spacecraft, the longer lifetime like JPSS, and here's a picture of JPSS with ATMS mounted on it. You can see the size of ATMS, 75 kilograms, 100 watts, and pretty expensive. This is from the NASA Tempest mission, which was actually a proof of concept for what became Tropics. I think you could say it's a very similar sensor. And then the size of one of these small sensors, this is what makes them cheaper and able to launch more, down to 4 kilograms and 6 watts of power. So some real achievements on that. And just 2 weeks ago, the 3rd and 4th Tropics CubeSats got off the ground from New Zealand. So there's now 4 of those in orbit. So that we may be able to start seeing some interesting data from that over the next few months. So I show this type of diagram every time I talk about the blended satellite products. It's a kind of a clock diagram with local time and the daylight portion at the bottom and the night at the top. And these are the low Earth orbiting satellites we're using are in sun synchronous orbit, so they come over at the same local time every day. And there's really two two planes that are the dominant ones right now, the 1330 plane with SUMI NPP and NOAA 20 and 21, and then the 0930 in the morning plane with the METOP plane. But NOAA has plans to launch something called Quick Sounder to fill in this gap here. There's like an 8-hour gap. Quick Sounder will be on orbit very close to the terminator, so it'll fill that gap in where otherwise we don't have new data. So what we end up doing is advecting or moving along older data. And with water vapor, it does change that, the atmosphere is there's uplift and sources and sinks of moisture. Certainly not as fast as clouds or precipitation, but having something else to provide an update in that plane will really help. But the beauty of the Advected products is it gives forecasters something to look at every hour, because in the past, if you were at a forecast office and the METOP data came by, you would have to wait about like 8 or 9 hours until you had any new data at all. So at least we can sort of make a more forecaster-friendly product. And then I just mentioned here, small sats are always welcome. They may not be in polar orbits, but they could help provide extra sampling on these diagrams. And just the same diagram for TPW, and this is for the current operational constellation. We use a lot more sensors there because some of them, like the GCOM and the GPM sensor, can only measure total column water vapor. They can't measure the profile. So there's more sensors that can do TPW. And then this is driven by the MIRS system, which really leverages heavily this 183 gigahertz data, which is a water vapor absorption band. So there's several channels there that can do the profile. And its key feature of the MIRS data is it's forecast model independent. So we're not sort of propagating the let's say the GFS solution back into this. So it gives forecasters an independent look at the water vapor structure. So I mentioned the TPW field. This is the new product that's going to go operational in early 2024. And what forecasters will see is down here in the lower left. They don't need to see all the components that go in, although maybe some of those are used anyway. I know like the GPS data can just be used separately. But this data takes the mimic field, so the kind of the microwave field from the upper left, which of course doesn't have isn't screened out by clouds. There's some precipitation areas. And then with the GOES data, which is actually quite high quality for TPW, we validated it in several ways, and the groups at SIMS, like Tim Schmidt's group, have also validated it. So where we have it, it's actually a very high quality field. So, but even here, like you can see the mimic over the Gulf of Mexico and the GOES, they sort of do capture this little channel of drier air over the Gulf independently. So, and then we bring in the GPS data, which is a sparser network, somewhere around 600 stations per hour over CONUS, but it's really important for sort of high impact weather events where it's certainly cloudy and also precipitating. It can fill in there. So so all that will be brought together in this new, what we call version 4.0 product there. So now I just wanted to shift to some of the experimental products that we're deriving from ALPW. This is all work supported by the JPSS Proving Ground and Risk Reduction Program. So a view with the polar projection, the historical record that we're looking at for 10 years. I don't call that a climatology. It's 10 years, but it's something about where events fit in the recent history. Layered vapor transport, and then some other work we're doing. I'm not going to talk about extracting wind vectors from this data. That's probably a whole other seminar. So probably something forecasters haven't seen much, and certainly don't need to over the CONUS. But these are actually global products that we're transitioning. Um, so they'll be able to look at big events in other parts of the world. Sheldon on our team here is already doing this. We pretty often get contacted by people from other Europe or Asia, other parts of the world when there's been like a flood event, wanting to know, where did the moisture come from, and what made that event so extreme. So just to keep that in mind, that these are global products. And right now, for instance, the international desk at WPC is using the ALPW over South America for forecasting, and we're also distributing this to the Brazilian Space Agency. So just a little different view here. This is the CONUS at the bottom, with a view of the Arctic. I think this is back in March here, but the polar stereographic projection, you can really see these atmospheric rivers that come into the Arctic. And one of the very first slides, there's a lot of research or findings that these atmospheric rivers are actually very important in sort of warming things up and melting, increasing the melt rate of sea ice there. Not only because of probably a little warmer atmosphere that's brought up with them, but the clouds that keep the infrared radiation from leaving to space and warm things. So there's sort of a weather climate linkage with these things. So I have my my last slide will have a page of links, but I have some here. These are just some different rotations here, going 90 degrees each time, to kind of see what these products look like. And actually over Russia, there's a big flow of water vapor at that level. So this is on the web if you want to see something further north. And for instance, the forecasters up in Alaska, I think, would be interested in that. So just a little bit of what we're doing with our record of data. We started producing LPW. It wasn't advected. It was just a layered product back in 2013. So we have about 10 years of data. So with that, we've started to experiment with some products to evaluate how current events stand with respect to the recent history. But there's a few interesting things in these climatologies. I have an arrow here at the 7 to 500 millibar layer. Kind of this area over Mexico, we often see, actually even going back to the ITCC, but plumes of water vapor that fuel heavy precipitation events. And Chris Gittro has published on this, sort of these very long distance transports of water vapor that can sort of make the difference between a sort of a normal precipitation event and maybe an extreme event. And just for reference, here's the June climatology, so you can see everything gets to be a lot more, and you really can start to see the sort of these source areas down in the southern areas, how much more moisture there is, and then how that looks with respect to climatology. And I kind of have a foot in the weather and climate worlds. I've worked on both kinds of projects, and I'm always fond of saying that doing any kind of climate research is very valuable for weather, just from the standpoint of quality of your products. So if there was some sort of bias in the products, like let's say it wasn't right over coastlines, or some artifacts, you could start to see them in a climate product that you wouldn't see in just day-to-day weather. And then vice versa, you see things in weather products that get blurred out in climate. So I think doing these types of things together really make a lot of sense. And just as an example of that, really as something from a developer standpoint, this is going through all of that data and just picking out the maximum for the entire for every grid point. And this kind of tells us some things like, do we have any bad data in there? And then that's always important to troubleshoot. Why was it something in our algorithm that is wrong? Is there something in the quality control of the data that we need to tell the developers about. So here's just an example. This area over the northern U.S. just looks suspicious, and since we're doing the maximum, we can go back and extract the individual granules out and really dive into that. And there's just another example here over the Pacific at the 850 to 700. So just the take-home message is just doing climate to support weather products really goes together. And this is back to this case. Some of you probably remember one of the many atmospheric rivers impacting California this winter for March the 9th, a big atmospheric river coming out of the tropics that really manifests at the lowest layers, the lowest 3 layers, and not quite so much above 500 millibars. That's kind of typical of atmospheric rivers. They're a little lower level. But what we've done with that 10-year record is come up with a percentile ranking. Where do these plumes fit? And the idea is that this would really give forecasters and probably the public as well sort of a message about how extreme these events are. And this all fits in, sort of complements the work on the like the atmospheric river intensity scale you've probably heard of that Marty Ralph's group has developed. All things that I think make the communication to the public easier. And these products, these percentile rankings, are being evaluated this summer, actually today, at the WPC FAIR experiment for situational awareness. So this was, certainly did turn into an extreme event with a lot of flooding in the Central Valley. And then another thing that we're evaluating currently is layered vapor transport. I think forecasters are pretty familiar with what's called IVT, or integrated vapor transport, which is typically done by taking the model through the entire column, or at least up to say 300 millibars, and then you sort of combine the winds and the amount of water vapor into a sum that gives you an integrated transport product, and the units of that turn out to be kilograms per meter per second. But what we're doing here, we already have the ALPW product, which the water vapor portion is independent of the model. So we're looking at these 4 layers, and the question is there value of being able to resolve that vertically? So rather than having IVT, we have layered vapor transport, or LVT, and that's being evaluated this summer as well. So we'll get a really like almost like a scorecard on this, or a report card of what it works, what doesn't work, what we could improve, those kinds of things. But the winds on this are from GFS winds. I did say we're doing some work on deriving our winds just from the microwave data, but we have not put those in here yet. So strictly with GFS winds. And then some other work, the MERS group that supports the operations and also does their own science at the University of Maryland at another cooperative institute, CSES, is reprocessing some of the data. So I'm just going to flip back and forth between these two, because with a newer science version of the MERS retrievals. So you can kind of see some of the differences. These aren't supposed to be the same time. These are just daily fields. So there's some time differences. But one thing that stood out to us right away is at the lower level, there's a lot more moisture in the reprocessed data. So we're going back to look at that well, is that valid? And then how does that affect the record of things? So but the CSES group is going to have an entire reprocessed record of SNPP and NOAA 20 that we're going to bring into SIRA and include in some of these climate type fields that we're developing. Let's see. I have a page of links here. I won't go into these now, but they can certainly be available to everyone. But just what I showed, the percentile indexes, the vapor transport, that stereographic projection, reduced size global 4-panel loop. The full size loop is like 5 by 10,000 pixels, so it's kind of large. But then we do have just a static static 4-panel global image we can look at too. So, and Sheldon looks at that all the time, like I said, for floods in all kinds of parts of the world. And we do have this training on the ALPW that's been available, and Dan Bykos has done some of the visit training sessions with these as well. So, so those are available. So just to wrap up here, a couple of take-home messages, then we'll have some questions. So these observationally driven water vapor data sets are I'm not a forecaster, but forecasters tell me they're useful, and they really show the plumbing of the atmosphere. And since TPW is increasing and more extreme precipitation events seem to be happening, there's just a big connection there that this is really the fuel for these events. Actually, this says new operational product available mid-2023. That's going to have to be late 2023 now, and same with the upgrade. So, so we should have both of these fully operational in 6 to 9 months, I think. We've already delivered everything. It's just on hold for some other things that are being processed. So it's not delayed due to technical problems. So then we're working on all these things about historical context of extreme events and transport. And then Sheldon has many applications of these floods, and winter weather is something that we're quite interested in, and really still gathering more cases on that. So so one question I have here that folks can think about is, will we ever get to a point where Oling model water vapor fields are needed? I mean, all these things I showed, a model can generate all of these types of fields, but without with all the other sort of I guess you could say baggage that comes with the model, all the other constraints it may have. So these are just direct retrievals using the radiance data. So that was kind of our purpose here, making these. And in the future we may see the models become, I guess, more trustworthy. I mean, I think they do quite well over the CONUS now, but some parts of the world not as well. And there's many science and data assimilation issues with that. NOAA has there's actually multi-agency joint center for satellite data assimilation to really look at getting all this data into the models. So so let's see. I think with that, I'll stop, and we can take questions. So thank you.
All right, John, I could listen to presentations about layered precipitable water all day long, but as you know, right? So now that John's given us a great presentation, I'd like to encourage everybody to please stay on the line for the discussion, and we actively encourage participation from field offices within the National Weather Service, as well as regional headquarters offices within the National Weather Service as well. And as you guys post questions in the chat room, we encourage everybody to use your full name so that we can give you credit when we go ahead and read your question online. And also, we are going to be posting a feedback survey in the chat room as well. Emily will be doing that momentarily. So go for a week from today, on Thursday, June 15th at noon Eastern Time, Jen Delamari and Ken Deerking from the University of Alaska Fairbanks will give a presentation for next week's Satellite Book Club based on the Alaska river flood impacts. And we also encourage everybody who is interested to contact TARS team of Kashad Bowman, Emily Maddox, for any questions that you might have regarding the Satellite Book Club, or for any configuration questions that you have for satellite products and AWIPS. I'd also like to remind attendees to submit their questions or indicate if you would like to ask a question verbally in the chat room. We'd be happy to call on you. And John, we're going to go right into questions now. I see several questions in the chat room, and we'll just start from the top and head down. So first is from Stephen Goodman, and he asks, he says, John, are there findings from your reprocessing that also apply to ABI GOES-R that is undergoing reprocessing since the start of the mission?
Yeah, thanks, Steve. Yeah, not specifically. We've been using the sort of the operational science TPW retrievals from GOES-R, what's called the legacy atmospheric profile. But if there is reprocessed ABI data, we could certainly build that into a climatology. But the records that I showed are not from GOES-R, they're from just the microwave sensors.
All right. Next question is from Bill Sorberg. What kind of feedback are you getting from weather forecast offices on the use of ALPW data for operations?
Yeah, I mean, we get a lot. I guess the most common feedback I get, since it's not operational, is if it's down, I start to get a lot of emails of where is it. So I know that people are looking at it. It shows up in AFDs. The National Hurricane Center uses it. WPC, I would say, maybe is the lead user. It's very, very heavily used there. And it even looks like there's maybe the next comment is from a WFO perspective. So we get lots of feedback, and the ALPW, we first started demonstrating it in late 2016. So we've had quite a few years to build this up, and it's going to 27 WFOs right now, not all of them, and those national centers. So it's kind of pseudo operational, I guess you would say.
Yeah, and speaking of, Randy Bowers, puts in a great comment and a question. He thought that the ALPW was baseline for AWIPS now, but it's not as of yet, but that's coming online here in the not too distant future, correct?
Yes, that's right. Like I say, I had hoped it'd be this summer, but due to other delays on the transition side, it's probably looking like a New Year's type situation.
Fair. Okay. All right. And Bill has another question. He says, do you have any formal feedback mechanism that forecasters can take to submit feedback on this initiative?
Well, when we participate in one of these experiments, like the FAIR experiment, and we've also participated in the hazardous weather test bed at WPC. Yeah, those we get a formal report from that, and some sort of grades, I guess you could say. But we're also very much like to hear from forecasters, and Dan Bykos and Sheldon in particular really reach out and get that. So we get formal and informal. But I'm always happy just to get an email if somebody uses it or doesn't understand it or see something odd. I mean, I'm always happy to get weather service type emails about the products.
Sure, absolutely. And Steve, I see your comment. I apologize if I called on you incorrectly there. Sheldon adds a comment here. He states that feedback depends on whether forecast offices put the products in their AWIPS. I know several offices have. When it goes operational, all forecasters will be able to see it and hopefully be able to provide more feedback. I think that's a great comment, Sheldon. And then Randy Bowers also asked, he's curious to know what might be expected, or what might we expect to be the advantage of LVT over ALPW, and he's looking forward to the results and the evaluation of this.
Yeah, that's a good question. Our hypothesis is that for probably really for more synoptically forced situations, not where just the amount of moisture is important, like maybe more summertime convection over the CONUS, but like for an atmospheric river situation, especially like on the West Coast or Alaska, where you have a plume of moisture impinging against the mountains, against the Sierras or the Cascades or any coastal ranges, that will we see like a large amount of transport in the lower layer that's not going to make it over the mountains, or on the other hand, could it be that there's actually more transport at higher level, which might mean that the moisture gets inland more? But this is a sort of a new product being evaluated, and it's the first evaluation is at FAIR this summer. So we'll see if maybe they're going to come up with some new findings that we don't know about. So good question.
Absolutely. And John, just out of curiosity, how much further back in time can we create a climate record of the layered precipitable water data?
Yeah, that's a good question. Well, if strictly from microwave sensors, the first sensors were something called SSMT2, which began in 1991. that hasn't been connected to these records, and then there's sort of a lineage there going to the AMSU data, and then into ATMS, and now I guess now into even some of the small sat sensors. So roughly 30 years from those microwave records. But I would mention we did just got notified we're going to start on something with the Climate Program Office to take look at like reanalysis and radio sound records that you can go back even further. I'm sure a lot of forecasters are familiar with the SBC sounding climatology, which is really geared towards severe weather. So we want to look at something like that, at least from the radio sound record, with more sort of flood-oriented fields, maybe some of the more water vapor fields, and connect those to flooding. And then, of course, with the radio sounds, you could go back to with a lot of quality control, maybe back to the 1950s, 1960s even. So, and certainly to like the 1980s with sort of a more consistent record. So it sort of depends if you want the strictly satellite or you want to look at other sources as well. But going back before 2013, which is what we have now, is certainly feasible. Okay. Are there any other questions?
Yep, Mark put a comment in here about getting the links for looking at this data outside of AWIPS. Mark, we're working on that. We'll try to post those links in the chat room here. And then
Yes.
Sheldon also put a comment in here. He says, I just sent a PowerPoint to forecasters in Kentucky showing the value of ALPW with the heavy rain, historic flooding that occurred there in July of 2022. The importance of satellite signatures of atmospheric rivers at the mid and high levels was very important to pointing out floods then. And Sheldon, that kind of goes back to the paper we published with regards to the West Virginia 2016 flood event too. I think we saw really long transport of mid and upper level moisture across pretty much the entire CONUS.
Yep. Yep.
Yeah,
So,
that's right. I think, I might say the sort of the number one forecaster impact of the ALPW product is just what you mentioned, Chris, that long distance, mid and upper level transport that we weren't really able to see very well before. I think that's been the biggest contribution, at least in my mind.
yes, absolutely. That's something that I was just totally mesmerized by when we were working on that paper together. So I think we're getting close to the end here. Let's see, Andrew's got a comment here. We have 6 weeks of forecaster evaluations that will make up fair this session or this season at WPC. He will be involved in the experiment for week 3, and I know Andrew's very interested in ALPW imagery. I will especially be looking forward to seeing how the LVT and historic LPW products connect to extreme rainfall events. Great work, John. And then from Jonathan Howell, I think, Sheldon, can you provide these research links of case studies in a common location so that anyone that's interested might be able to access them?
Yeah, I think, I think that's a great idea, and I'll work with Sheldon. We can put them on a web server. So yes, that we'll follow up on that one. That's a good suggestion.
A lot of those cases are on the Sierra website under the visit program, but I'll try to send you the link for that. There's a number of cases on there that I worked with Dan Bikos on.
Yeah, thanks, Sheldon.
Absolutely. Thank you, Sheldon. And I think we're kind of wrapping it up with regards to questions. So at this time, I'd like to go ahead and hand it back over to Jordan.
Thank you so much, Chris. And thank you, John, for that great presentation. I really, as Chris said, Total Precipitable Water is very beneficial, and I really enjoyed hearing the latest on this important product that we get from satellite data. Please join us next week for all of those of you that are on the call. Jen Delamere and Carl Durkin from University of Alaska Fairbanks-Jena are going to be talking about Alaska River flood impacts. They do things a little differently up there in Alaska, highly reliant on the satellite data. So hope that might be an interesting topic, even if you are not at higher latitudes. In the meantime, if you have any questions about the configuration of satellite products in AWIPS or about the Satellite Book Club, please feel free to get in touch with Kishad or Emily. They are there to help, so please send them email. With that, we'll wrap it up for today. Thanks again to our presenter, our facilitator, and all of you for attending. Please have a great summer. Take care.